And we knew we wanted to run it on that TX2 that I was showing you. That was kind of what we were using for this course. Cool. So installing the TensorFlow Object Detection API. My first recommendation is that if you don't need to, don't. Just skip it and get the Docker file. So here at TensorFlow, you'll find all of their object detection stuff under Models, Research, Object Detection, and then the Docker file itself under Docker Files, Android Docker file. That makes it so much easier. Otherwise, you can find like a lot of setups, but you're installing a lot of libraries, and people are having a lot of problems getting this stuff installed. Also, it's worth just exploring this repo. There's a lot of the utilities that we'll look at a little bit. You'll find here, and you can dig into and modify as necessary. The one change that I needed to make in here is this is their like yes and no's to a lot of the configuration files. I had to like modify that. So if you're doing this, you might need to play whack-a-mole with no's and yeses and new lines to get that installed. All right. So looking at training. So first you need to convert your data to TF records, which, Pascal is that nice human readable format. Here, the TF records, they're binarized serial files, usually sharded. So that was kind of one thing that I found like initially a little bit confusing when first diving into TensorFlow, was just getting that transition nice and clean. Basically what you're trying to do is just, for each of your features, you're trying to have a little dictionary with a string of the feature name, and then a TensorFlow feature vector, right? So, this is, you'll just convert the XML into a dictionary. This isn't really anything that special. This is just like a recursive parse to dict. And then here we start looking at this is also the opportunity to make some transformations that you'll need to make in a TF record. So for example, just call out a few things. So a lot of things will give you this opportunity to ignore difficult instances. So if your model is performing too badly and you just want to ignore the ones that you've labeled as hard, you can kind of flip that flag and ignore stuff. Otherwise, it's going to go through that XML, get the bounding boxes, get the mins and the maxes of the ground truth bounding boxes that you've labeled, and then divides them by the width and the height, so that you're actually just dealing with a float between 0 and 1. Otherwise, not too much there. And then for images, you're just reading the binary file. So in Python here, you're using this TensorFlow gfile utility, and you're just reading in the binary as opposed to just like a regular read there, and that's your encoded JPEG. And then here we actually define this feature dict, where we, for each of our attributes, I'm just kind of showing some of the different kinds of features, right? So there's like an int feature, the bytes feature. This is for the strings here, the encoded strings. Then you've got some lists, right? Because each image could have a list of multiple xmins, and multiple classes here. And the encoded image is also in bytes. And then you just pass that to this TF train. You sort of give it to this example class, and give it the features, and then that builds your example, which is what you use then to create, and you use this utility. I mean, I guess that's one of the things that I want to emphasize or whatever when dealing with this, with TensorFlow, especially these object detection things, is you really kind of have to lean on the utilities that they provide to kind of make all this stuff happen, or else you're going even more into the weeds and making your life more painful than it needs to be. Cool. So after we've written the TF records and kind of gotten our data ready to go, now it's time for us to download that pre-trained model from which to do transform learning. And here again, it's very nice. There's like a whole model zoo. If you just Google object detection, detection model zoo, you'll find all of these different COCO trained models, which you can try. That's one of the great things, is like once you've set up this pipeline, you can try a bunch of different models. With the obviously different map. Map is the mean average precision, is the metric by which a lot of these object detection models are evaluated, which basically looks at the amount of overlap of the boxes you've predicted and the boxes that are like in your ground truth file. So we primarily worked off of this, the ResNet 50 with, I think, the focal pyramid network that was trained previously on the COCO dataset as our base model here. All right, and what do you get when you download one of those models? You get a folder like this, and we'll kind of keep coming back to this file structure just to talk a little bit more about what all these different files are. But first, we're going to dive into the pipeline.config. So here is where you get to specify a lot of parameters for training and evaluation. And actually, when we talk at the end about like the future of TensorFlow and production and where that's going, this config file is kind of like rising to even more prominence, I think, in where they see things going. Okay, so we're peeking into that. One line I highlighted here is like this config is TPU compatible, right? Some of the models are more TPU. So TPUs are Google's new tensor processing units, which are, it's a separate model architecture or hardware architecture entirely from GPUs, right? Which are normally used for these graphics, calculations, right? They can do a lot of matrix math in parallel. So some of them are identified as that. So if that's something you want to take advantage of, then that's nice to see. And they're just like right at the top, in the comments there. So then we're getting some, it's defining a model. It's a single shot detector. Is what that SSD is. Some other cool features: the anchor generator. So anchors in an object detection model are so basically like at each point, it will consider whether or not it has things that match within each of these boxes. They're always hard for me to explain, but like, so for example, if there's a person standing here, they would fit in that taller box. If there was a car in this image, that might be detected by this wider box. And then of course, so you've got like those kind of patterns of like aspect ratios, and then different octaves of like, a small person or a car, or like a medium-sized one, or a larger one in the frame. And I really love that they actually like let you do some configuration of the anchor generator in the pipeline file. And then also this image resizer makes it really handy, where you just kind of put in, obviously the height and width of the images that your model is expecting, and that will, when the model is given something else, it will resize to those pixels or add the buffers that it needs so that it can like deal with things of different sizes. What did I want to show on this one? Oh yeah, you know how I talked about like we had manually generated those horizontal flips to be able to get more training examples. They also include some data augmentation options. So you can just plug in and say like, give me some like random horizontal flips. And then also randomly cropping in an image, which is another way of like augmenting the number of training examples that you have by having it like automatically scale up and scale down essentially some of the images by cropping into them. So those are cool things. And then like, so now we're back out of that pipeline config file, back in the training script. And we see like you can kind of just like identify, download a few models, and then just in your actual script, I'm not going to go through all this, but like just basically switch out which one you're using, right? So like once you've got things defined, you can go into the pipeline files of each one of those and tell it where to get your, tell it which checkpoint you're training from. So it does make it a little bit easy to like actually switch out and try out different models. And then finally, training, which you can use the model main script in the object detection folder from that repo that we looked at earlier, or you can actually train online via the TPUs, which are currently just available online, or up until recently were only available online. Now you can actually get these new Coral TPU dev kits and stuff and have your own, but those are just small ones really. And actually this code is still using ML Engine. I mean, as Rami mentioned, like this ecosystem is changing really fast. Like all of these commands, like ML Engine is now AI platform. So we'll talk about that too. But training online is pretty cool. It's nice that you can do that and you can just monitor the jobs from the, Google Cloud Console AI platform, see the jobs there. All right, and then you export your inference graph. So that's the first flavor of freezing your model to now actually be able to use it in prediction that we'll look at. So when you freeze that, you get your own version of basically what you downloaded earlier with like a data zero and the frozen inference graph file. Okay, so now you've got a trained model. How are you going to do something with it? Oh yeah, so let's take a look at this guy. So I think that actually starts here. So here we see some test footage. Now, interestingly enough, this model does not do a very good job with hard hats. This is on the ResNet 50 one, and then we'll look at the YOLO trained one next. But you see it gets people, it gets safety vests pretty well. It gets the green ones better than the orange ones. Gets that guy coming in. Some things are like, even in annotating, right, we have to decide like, well, what makes a safety vest, right? There's so many different flavors, and some people are wearing full body things, some people are wearing upper body things. We decided to go just with upper body. Okay, cool, so that's that one. Now let's look at the YOLO one that we had previously trained, which does a lot better job with the hard hats. And this one only samples once every 5 seconds, so you see those boxes kind of lingering, right? Because that's what we were planning on doing. Is, we don't need really every frame. We just need to check these construction sites. So now you see like the dark green boxes means like it thinks somebody's good. The red box means it thinks somebody's bad. So all those people that were walking across the bottom doesn't think they're in compliance. These guys currently, it thinks they're in compliance. There's like a false positive of an anomaly detection there. Which is one of the reasons we wanted to kind of like smooth things out, right, and just have to see a bunch in a row that are wrong before it gets it right. Yeah, okay. So that's where it is so far, which we're hoping we can take, or maybe we'll do another round of training on it a little bit more before we actually pitch it to some of these companies. But we're trying to hope it to go in that direction. All right, now let's talk about deploying on edge. So here's kind of this first architecture that we're considering, right? So we've got the job site at the bottom, and we've got like a bunch of different edge cameras that each would have their own compute, right? They would each be connected to one of these TX2s. Uh-oh, I think I just pulled, no, that's just the USB shielding. Okay, so each camera would have its own compute, right? Which one of the pluses of that is that you're like, got somewhat fixed processing costs, right? Like you've already paid for this compute, it's out there. As long as that camera doesn't break, you've got some compute happening. And then you would send up your detection results as well as frame grabs for future training, right? Because like if you do just all of your compute here and just send up your results, then you're not really able to refine your model as you move forward. So you would want to send those up, but if you're only grabbing the frame once every 5 seconds, right, you're saving yourself a lot of bandwidth and stuff like that. So just send that up now and then periodically retrain in the cloud. And of course, just have the alerts sent to the supervisor as needed. But okay, so to run on these NVIDIA devices, you need to convert to Tensor Rt. So that's kind of one of the other little technologies we're looking at today. So Tensor Rt is from NVIDIA, but it's meant to be basically to make TensorFlow models like run smoothly and nicely on NVIDIA hardware, on NVIDIA GPUs. So for example, this graph shows lower is better here. This is just running a regular TensorFlow model on the NVIDIA Jetson Nano, which is like the smaller new $99 version of the TX2. And then this is like that same model run on once it's been converted to the Tensor Rt hardware. And now we're zooming out. This is like that larger graph to contextualize further. So this would be like a Raspberry Pi on its own. The Jetson Nano just with TensorFlow is only like not even twice as good as the Raspberry Pi on its own, right? You really need to do that hardware optimization to get that performance on the GPU. Interestingly enough, we were talking earlier, I was talking with Abe earlier, these are the new Coral, the Coral dev board and the Coral USB accelerator that are like super comparable in performance. So maybe you don't need the Tensor Rt stuff as much if you're going with that TPU situation. So something to think about. But what does Tensor Rt do? So it quantizes models, which is actually something you can also put in that pipeline config file we looked at earlier. which changes all the floats to, it quantizes them to 8-bit integers, but still apparently does not really dramatically drop your accuracy. And it does some other optimizations that I don't even pretend to know everything that it does. But it dramatically, it does speed up your hardware, and it's something that Google is actually embracing as well, and they talked about at their TensorFlow Dev Summit. We'll talk later on about where that plays in. So to convert to Tensor Rt, you can pull this tensorflow.contrib Tensor Rt library, and you you convert it to the Tensor Rt graph, and write that out, serialize that. All right, but what if your work isn't on the edge? So now we'll leave behind deploying on the NVIDIA hardware, and we'll look at deploying in the cloud. So as we talked about, the ML engine has become AI platform. Like, that's the first thing we're going to look at, just because it's kind of like the easiest. If you just want to deploy a model that runs every once in a while, so for example, for this like text situation tonight, that's what it's on, because I didn't want to like leave this Kubernetes cluster up and running and whatever, and how fun just to be able to have this thing, and like I can occasionally talk about it and have somebody text something in, and it'll just like spin up an instance, run the model, shoot that back, and then you don't have to pay for it when it's not like in use. So it's kind of handy for stuff like that. Right, so the architecture here, right, the text message goes in. I'm using SignalWire, which is like Twilio, and this LAML API, I guess, and it goes through a Google Cloud function that calls AI platform and returns the image. But for all of the stuff that we're talking about from now on, that frozen inference graph, when we exported the model earlier, won't cut it. We need variables in that variables folder. So we have to get this saved model format via TensorFlow train saver save. And this is what like TensorFlow moving forward is kind of clearly leaning towards. They're going to make it easier to do this in the future. But for right now, it was kind of a pain actually to like get the saved model format out with variables in this variables folder that you know is part of what you export here. Okay, but a cool thing is that when you do have it in the saved model format, there's this saved model command line inspector with a show argument or function, and you just give it the path to the model and this all flag, and it can like show you a lot of stuff about your model. So it'll give you like what are your inputs, what are your outputs, that make up the detection signature, because for a lot of things you're passing it, you need to know the names of the input that it's expecting, as well as the outputs and stuff. So that command line inspector is pretty cool, and it can also start converting. They're like adding that, so we'll look at that a little bit later. And so in this blog post, this how to deploy an object detection model with TensorFlow Serving, this guy Gaurav Kela gave a great. He gives some instructions for modifying the existing utilities to export an object detection model to that saved model format while including the variables. So, yeah, okay, so, okay, and the other thing I want to talk about, so if you are planning on serving it like online or something, you'll want to change your input type there from image tensor, which is just expecting actually just like the image array, right? It's expecting the NumPy array of the 3 channels that you're sending it. But if you change it to this encoded image string tensor, now you can just actually encode your JPEG space 64 bytes and send that over. So for actually like sending it over from like the Google Cloud function, it wouldn't even send out the bytes like big enough to do this. So by switching it over to this encoded image string tensor, you actually get it's just a lot more performant, obviously, and network friendly. And now you can test the model locally. So once you've got it in the saved model format, you can use the gcloud AI platform local predict, point it to your model directory, give it a JSON instance that would mimic the queries that you would send to it, tell it the framework TensorFlow, and you can just do those predictions locally, which is of course something you want to do before you actually upload it, where you'll upload it into Google storage And then you can load it as a model in AI platform. And just to like talk about the hierarchy that they use there, you create a model which is like safety monitor, right? It's like what we're going to be seeing multiple versions of. What actually runs is one version. So yeah, so your model is kind of like the larger hierarchical structure, and then the version is what runs underneath that. Okay, and now making the request. So as I mentioned to you, now because we set that input into the encoded format, we can actually encode our image in base64 with this base64, B64 encode. You pass it the image that you've read, and then just decode the string that comes out of that. So that's a UTF string. And then here's the JSON payload structure that Google wants. So you put it in a dictionary that first needs the string instances, and then that is a list which includes each one of your instances as its own dict. And if it would be inputs using our model, using the ResNet model, and then the unencoded just image array of the NumPy array of the image. But when you're sending it the encoded bytes, you have to name this B64 so it knows to unencode that. Okay. So, and then actually making the request isn't that hard. You just now you're using this Google API client library. You're telling it to build this ML version 1. Those parameters, right? And then this is like the hierarchy directory that it needs, right? Projects, so your project name, models, followed by the model name. You can then pass also another like / versions and give it a specific version if you don't want to just use the default version. So that's like a good way of like testing a new version or something if you want to like serve that just to some people, and then you make the request here. Okay, so here's like one of those images that we see from that. So, here we're actually getting hard hats okay for a bunch of them, except these guys over here. We're also losing the people who are truncated or more obscured, but we're getting a bunch of those guys in the middle. Okay, so also on AI platform, you can create some custom prediction runtimes to host Keras, scikit-learn, or XGBoost models. So, that's cool too. All right, so now deploying on if you want to deploy on your own cloud, right, in a Kubernetes cluster. So this is if we are right. So we've got some like application that would just call the model in our own pod, and now we're going to use TF serving, another one of those many things that start with the name TensorFlow. So they actually make that part super easy. Again, once you've got that saved model file, you just, so you're building a container, a Docker container here from the TensorFlow Serving container, passing it the environment variable of a model name and telling it which model you want to be running. And then you just need to make sure that model is in the containers models directory with that same name that you're passing as the model name. And so you can do that in a couple different ways. So like right here, right, just to kind of test it out, we're running it and we're mounting a volume with like, this is our, hosting computer's path to that model file, and then we're giving it the alias models safety monitor there. Yeah, cool. And what you're actually pointing it to, this was kind of confusing. I don't know, this isn't very clearly in the docs. So you're wanting to point it to this higher level parent directory in terms of what is your path to your model here. And then you have to rename this to 1. This needs to be an integer number, and then it just by default serves the highest integer number model. Okay, but actually if you're building this as your own container, it's actually super easy. This is like the entire Docker file that you would need to like build your own container with your own model. You just inherit from the TensorFlow serving thing, copy your model into the, there's a space there, sort of hard to see, into the models directory with your name, and then pass it the environment variable of the model name. And now that container is just ready to run, just expose a port on it, whatever, and you're serving the same, so now you just, go back, just build that container, and give it your own name or whatever, point it to that Docker file, and now you've got this container that includes the model in it and is ready to serve that. You would just run it by exposing a port. This is the container name we've given it. And then to make the request against it, we have this TensorFlow Serving APIs, just gives you these scripts. I mean, there's a few lines of code here, but not too bad to just build this predict request, pass it some of those same parameters that we've looked at before, and then execute that, give it a timeout and stuff like that. So the TensorFlow Serving, being able to serve a model from a container is pretty easy, pretty powerful. Obviously, you could then put that on a Kubernetes cluster, like with a load balance or whatever, and have a bunch of different copies of your model able to kind of serve the requests coming in. So that is super cool. And another really cool thing about that is, that Tensor Rt stuff to run on NVIDIA that we talked about before. So there is like a separate NVIDIA Docker runtime, and if you're running on hardware that has GPU acceleration, or if your Kubernetes cluster's there, you can actually use the NVIDIA Docker runtime with the privileged flag, which is what allows a container to access the GPU on the hardware that it's running. And then it can actually run like these Tensor Rt accelerated things, so you can actually get even more performance out of that, which they mentioned at the TensorFlow Dev Summit like a couple months ago. So that's really cool that they're like embracing it from that side too. Like NVIDIA was doing a lot of the legwork on that before, but and actually Google is also putting that saved model command line inspector that we looked at before. They've now added this saved model CLI convert function to actually just go ahead and straight and easily convert a saved model to Tensor Rt. So you just have to tell it that you want an additional tag set for Tensor Rt, and you can convert your model just with that. So that's pretty cool too. All right, and just as a bonus, because I had put it in the description, we'll talk about TF Lite as well. One more of these like ways you can deploy TensorFlow. I'm not going to go into it fully, but TF Lite is for mobile and IoT if it's not specifically like NVIDIA GPU accelerated. Same thing, like back to when we had this frozen inference graph version that we put out. Also, again, in the models research object detection area, there is an export TF Lite single shot detector graph file. So, you're just passing in what you're inputting. Here again, you could change that to the encoded type, and then pointing it to the pipeline file, the output directory, and the last trained checkpoint, which of course is this guy. You just put the path to that. You don't put the actual file, by the way. And then if you want to learn more about TensorFlow Lite, this TensorFlow for Poets 2 lab is pretty good and just talks you through. You can search it either for iOS or Android to get a working object detection model on the phone of your choice. Okay, so now we're going to peek ahead a little bit into the future. And see where TensorFlow is going. Obviously, TensorFlow 2 is coming out, so what are they thinking with this machine learning training on that? Is Kubeflow going away? Rami kind of foreshadowed that. So Kubeflow has been long trumpeted as this way of containerizing and handling this whole model pipeline. But Kubeflow code looks like this, where you're always starting with KS, which is referring to KSonnet. And KSonnet, while I was researching for this talk, actually, discovered this, that the team behind KSonnet is stepping back from the project. All work on KSonnet will end. So first I was like, why would they do that, right, as all this stuff is getting well adopted? But I think the answer is they probably knew that Google's kind of moving on to TFX. So TFX stands for TensorFlow Extended, which is what they're really trumpeting as their deployment solution for TensorFlow, which includes all these different modules that let you do some pretty cool stuff. And validate your model. For example, like this model validator takes in like your new model and your previous model and a bunch of test cases and make sure, it's like to make sure that you're not screwing any edge cases up all of a sudden, right? Like we want to make sure that like, you know, all these bias and things that are baked into a lot of these models, right? Like you can check it there to make sure you're not treating some class like horribly or something in that. And they give you a lot of different things to just, a lot of different modules. Like there's some cool YouTube videos on that. And then you push at the end of this pipeline to, as we talked about, TensorFlow Serving, which is a great way to run it in those containers we looked at. TensorFlow Hub is another new thing to like host a bunch of models. There's TensorFlow Lite or TensorFlow JS, JavaScript that Rami talked about, I think it was last time. So, and then remember that pipeline config file that we looked at that included like all of the stuff about different ways of evaluating and different like the anchors and all that stuff? That's going to be like this one big config file that will help take your model through the whole pipeline. So that's kind of my guess on like why the K-Sonnet guys got discouraged, is they might have known that like this was the direction that Google and TensorFlow were moving in. I mean, and if you notice, they're even really like, they're showing that you can like manage this TensorFlow extended pipeline on either Airflow or on Kubeflow. But I think like it's sort of telling that Kubeflow is in like this back tab, and they're actually putting Airflow forward, which is what they also use for their Google Cloud Composer. So that's my guess. I don't really know. I mean, there's parts of Kubeflow that are still really interesting, but I think more it's like you're seeing those parts being taken and used. For example, like Selden was what they would actually use in the Kubeflow configuration to deploy and serve a model, but now there's TensorFlow Serving, which does that pretty easily. So I kind of think ideas from that are being taken in other things. And like they're replacing K-Sonnet in Kubeflow with a tool called Customize with a K, but Customize is also built into the Cube control kind of command line anyway. So I think like that's my guess, is that Kubeflow is kind of being consumed from different directions and its ideas are being taken. And so we'll kind of still have that concept of like a macro system with this one configuration file that can kind of take your model all the way from training to a bunch of other things. So then this is just this is like the TensorFlow Dev Summit videos. So these were in March of this year. If you want to kind of see more about what's coming up, I would recommend you check this out. Like there's two really good videos on that TFX pipeline, like the pre-training pipeline and then the post-training pipeline, as well as a bunch of other cool things. Okay, so thank you. That's what I've got for today. Yeah, I guess we'll go to CU29 after. Or let me know if anybody has any questions as well. Yeah. Did anybody get any decent results from texting the thing? Or any interesting results? No. Cool. Uh-huh. It nailed it? Good. All right, good. Yeah. What's that? Yep. So Rami asked if this pipeline will support scikit-learn and XGBoost and all those things. I don't know, and that is like one of the questions that I have for it. But I know that they are supporting that in like the TensorFlow Serving and like AI platform stuff. And Keras obviously is being well embraced in TF2. But so in that way, I'm not sure that it replaces Kubeflow. But I'm not sure actually. Yeah.
So second question, in terms of model versioning. Mm-hmm.
Integer. So I know, that's really weird. So when you're like up on AI platform, right, you can actually like give the versions names and call them by name. When you are when you're deploying but to TensorFlow Serving itself, yeah, you have to like rename the save model folder to the highest integer. I don't know. I mean, I wonder, there must be a way to change that, right? Like I fully imagine that that's something I have not like discovered yet, or there's a different way of telling it which is the default save model. But yeah, but that's at least how it goes by default. So is that the main way, or other ways I know that like TF serving is like the main way that well, first of all, this saved model format is definitely what TensorFlow is like putting forward, and they've promised that in TF2, which is in alpha now, that there's going to be easier ways to export to that. But and then I think TensorFlow Serving, I mean, it is so easy just to get that, you know, like for this to be the whole Docker file, to be able to like put a model and have it accessible via an API, which is either like REST or gRPC, is like pretty cool, I think, and pretty easy. Yeah. Yeah. Oh, the anchors, what the anchors do? So yeah, the anchors, because when these single shot detectors, right, so they're running it through like a bunch of convolutional layers, and they're trying to like have all their features activated at once, or all the filters activated in one pass through the image. It needs to know, like, so for example, if you've got like a dog centered on this pixel or a dog centered on this pixel, like where to draw the box, right? And it draws it for the box that has like the highest confidence. This isn't true of all models, but like it's generally a helpful way to look at it. That like within one of these anchors, one pixel owns the one that has the highest confidence for that dog. So basically, these are like basically the sizes of items that are being looked at for this central pixel here, right? And then it would move over here, and all of these boxes would move over one pixel. But by giving it these boxes, it's able to see, and they do actually, after they find which box has the best fit, they restrict, the boxes do close in on it, right? So this doesn't have to be the final shape of the object that's detected. It will like shrink the boxes to fit it, but in terms of like it needs the big picture to look at. So that's why it generates all of these things. And this just kind of gives you like some good control, rather than like, for example, in YOLO, you just have to like type in the aspect ratios of all of your boxes in this anchor text file, and so you have to kind of basically do this code and like generate all those boxes separately. This gives you like a nice way, clean way of generating those. Yeah. Is there somebody? Yep. Sorry, can you ask that again? Yeah. Yeah, so he's asking about like how would you like update the edge cameras if you're using just like the Jetson on the edge. You would just use it for inference. You know, so you would they're you know, powerful for like running a real-time camera. I mean, you can train on them. We have trained things on them, but typically the workflow would be training something larger on the cloud on more powerful machines, and then just using these at inference time. Yeah. And of course, you would want to kind of continue training in the cloud and just replace the model on the device, you know, push an update to it as you have them out there in the field. I actually don't right now, and that's actually like something that we really need to do. I know, but I don't have those like map scores. I think on the YOLO model we did evaluate the stuff, and we actually got like our map score was like 76 overall, which was pretty good. But we haven't yet evaluated on the different, because we're still kind of playing with a few of these different TensorFlow models. Quite frankly, I think the YOLO one did better already. So I want to go back and try actually with MobileNet v2, because I think that I think the ResNet ultimately should do better, but I think it would need a lot more data. I think the MobileNet are their smaller models that are meant to be on like IoT and mobile devices, and I think with the such limited amount of data that we have, I think that those will actually perform better, and then I'll have the stomach to compare it. Yeah. Uh-huh. PyTorch, I don't really have that much experience in PyTorch. I've messed around with a little bit, but I don't really know. I guess the one thing I do know about, like a big thing coming with PyTorch, is their merging with Caffe, and that Caffe is known to be like have really fast deployment for vision models specifically. So the fact that like PyTorch is bringing that ability into the fold, I think is going to be pretty cool for them. Yeah. I don't know. Like, it seems like right now everybody's playing really nicely and like tries to support all the frameworks on every platform. So maybe they will, but not. Oh, sorry. So he asked if I thought that like TFX would support PyTorch, and my thought is like, I don't know. Right, the fact that it is just called TFX and has TF in the name, as opposed to just being like for AI platform isn't like the TensorFlow AI platform, so it can support. I don't think it can actually do PyTorch, but it can do some other Keras and scikit-learn and stuff. But yeah, so I guess I don't really know. That's the answer. Yeah. Cool. All right. Well, thank you guys so much, and yeah, see you 29.
So Andrew, I want to tell you, that was probably the best slide deck I've seen walking through both a very interesting project that wasn't simply classifying cats and dogs, but also very seriously walking through the code, but not too bogged down in the details. Cool. But that was very impressive. I'm going to steal your template. One thing I forgot to mention, so I work for a startup here in town called Novi Labs. We are looking for good people as well. We're looking for front-end and back-end. In particular, we're looking for machine learning engineers in addition to front-end and back-end. Hit me up after if you'd like to chat about a position. Let's go ahead and move over to CU29, and we can continue your conversation there. I think there's extra pizza left. Feel free to grab a slice or an entire box. I'm very serious. Let's not waste the pizza. All right. Have a good night.